Boeing could cut fuel costs by 10 to 15% with one wing design, and airlines could save billions every year. The technology exists right now, and researchers have proven it works repeatedly. So why is nobody using it? If this technology is so powerful, why is not Boeing already implementing it? What is stopping airlines from adopting innovations that could save massive amounts of money? Why do modern planes ignore a breakthrough that could make current designs obsolete? The answer reveals something fundamental about aviation. Efficiency alone does not determine success. Reliability matters more. And this revolutionary wing technology, despite its incredible potential, fails the reliability test catastrophically. This is laminar flow wing technology, and understanding why Boeing does not use it requires understanding what makes it both brilliant and completely impractical. The concept is elegant. Air flowing over a wing creates drag. The smoother that airflow, the less drag generated. Less drag means less fuel burned. The difference between smooth and turbulent airflow is the difference between efficiency and waste. In aerodynamics, we call smooth airflow laminar flow. Imagine air molecules moving in organized parallel layers, like pages of a book sliding smoothly past each other. Each layer flows orderly without mixing with adjacent layers. Turbulent flow is the opposite. Air molecules swirl chaotically, creating eddies and vortices. Think of smoke rising from a cigarette. Initially, it rises smoothly. Then it breaks into chaotic swirls. That transition from smooth to chaotic is laminar flow becoming turbulent. Aircraft wings experience both. Near the leading edge, airflow starts laminar. As air travels back across the wing, it transitions to turbulence. The boundary layer, the thin layer of air directly touching the wing surface, determines this transition. In laminar flow, the boundary layer remains thin and organized. In turbulent flow, it thickens and creates significantly more drag. The longer you can maintain laminar flow across the wing, the less drag you generate. NASA research indicates laminar flow wings can reduce drag by 10 to 15% compared to conventional designs. For commercial aviation, this is revolutionary. Fuel represents one of the largest operating costs for airlines. A 15% reduction in drag could translate to billions in annual savings industry-wide. So why are modern airliners not using this technology? The problem is extreme sensitivity. Laminar flow requires nearly perfect conditions to maintain. Any surface imperfection destroys it instantly. A bug hitting the wing, dust accumulation, rain droplets, ice formation, paint chips, rivets, panel joints. Any of these disrupts the smooth airflow and triggers transition to turbulence. Once turbulence starts, it spreads rapidly across the wing surface. The drag reduction disappears completely. You are left with a wing that costs more to manufacture but performs no better than conventional designs. Surface perfection becomes a maintenance nightmare. Wings must be cleaned constantly. Any contamination eliminates laminar flow benefits. Airlines operate in the real world with dust, insects, weather, and pollution. Maintaining the surface smoothness required for laminar flow under these conditions is extraordinarily difficult. Even manufacturing presents challenges. Conventional wings tolerate minor surface imperfections. Rivets create small bumps. Panel joints create tiny gaps. These imperfections have minimal impact on turbulent flow wings. But laminar flow wings cannot tolerate any imperfections. The surface must be perfectly smooth. This requires dramatically more expensive manufacturing processes, special materials, precision construction. Every rivet, every panel joint, every surface detail must be perfect. The performance becomes unpredictable. Airlines need consistency. They plan fuel loads based on predictable aircraft performance. An aircraft that achieves 15% drag reduction on clean days, but normal drag on dusty days, creates operational chaos. Flight planning becomes impossible. Do you fuel for the best case scenario and risk running short? Do you fuel for worst case and waste capacity? Airlines cannot operate efficiently with this uncertainty. This is why Boeing does not use laminar flow wings. Airlines do not just need efficiency, they need reliability. They need consistency. They need technology that works every single flight, regardless of conditions. But this does not mean researchers abandoned the concept. NASA has studied laminar flow since the 1930s. The National Advisory Committee for Aeronautics, NASA's predecessor, began experiments before World War II. Early research proved the concept worked. Laminar flow could reduce drag substantially under controlled conditions, but making it work on operational aircraft proved far more difficult. Engineers developed active systems to maintain laminar flow. These use tiny holes in the wing surface to suck air into the boundary layer. This suction controlled the boundary layer and delayed transition to turbulence. NASA tested boundary layer suction extensively. F-16 aircraft and other test platforms demonstrated the technology. It worked in testing. Drag reduced measurably. Fuel efficiency improved. But these systems proved too complex for commercial use. The tiny suction holes clogged easily. Dust, insects, and debris blocked them constantly. Maintenance requirements were excessive. The systems added weight that partially offset efficiency gains. The technology worked in perfect conditions. Clean wings, controlled environments, careful monitoring, but real-world operations destroyed the benefits quickly. This remained the situation for decades. Laminar flow represented a tantalizing possibility that never quite worked practically. Researchers understood the physics. They could demonstrate benefits in testing, but operational implementation remained elusive. Then, modern breakthroughs started changing the equation. Airbus launched the BLADE program under the European Union's Clean Sky Initiative. BLADE stands for Breakthrough Laminar Aircraft Demonstrator in Europe. The program tested laminar flow technology on an actual Airbus, A340, not in a laboratory, not on a small test aircraft, on a full-size commercial airliner in real flight conditions. BLADE achieved remarkable results, up to 50% reduction in wing friction in the laminar flow regions, around 5% fuel savings in realistic operational scenarios. This demonstrated laminar flow could work on commercial aircraft under certain conditions. The key was natural laminar flow wing design. Rather than using complex suction systems, engineers shaped the wing to promote laminar flow naturally. Careful contouring and precise shaping maintained smooth airflow without mechanical intervention. This approach eliminates the complex systems that plagued earlier attempts. No suction holes to clog, no pumps to maintain, just careful aerodynamic design promoting laminar flow through shape alone. NASA continues advancing the technology. In 2026, NASA tested laminar flow wings on an F-15 research aircraft. The goal was demonstrating approximately 10% fuel savings for large aircraft through practical laminar flow implementation. These tests explore wing designs that maintain laminar flow without extreme sensitivity to contamination. New shapes and surface treatments show promise for real-world durability. The technology is improving. Researchers are solving problems that made earlier implementations impractical. But significant challenges remain. Manufacturing costs stay high. Natural laminar flow wings require extremely precise shaping. Tolerances are tight. Production processes are expensive. These wings cost substantially more than conventional designs. Maintenance requirements, while reduced from active suction systems, remain significant. Wings still need careful cleaning. Surface damage still destroys laminar flow. Airlines must implement new maintenance procedures. Weather limitations persist. Heavy rain still disrupts laminar flow. Ice formation remains problematic. Operating in contaminated environments reduces benefits. The question becomes whether benefits justify costs and complications. A 5 to 10% fuel savings is substantial. But if achieving it requires doubling wing manufacturing costs and implementing expensive maintenance programs, does it make economic sense? Airlines operate on thin margins. They need solutions that improve bottom lines clearly. Laminar flow technology must prove it saves more money than it costs before widespread adoption becomes realistic. Boeing evaluates all these factors. The company watches Airbus BLADE results closely. They monitor NASA research carefully. Boeing understands laminar flow potential thoroughly. But Boeing also understands operational realities. Airlines need aircraft that work reliably every day in all conditions. Technology that delivers spectacular results sometimes, but fails other times, does not serve customers well. This is the real reason Boeing does not use laminar flow wings currently. not because the technology does not work, but because it does not work reliably enough under real operating conditions to justify costs and complexity. However, this may change soon. If new designs succeed in making laminar flow more robust and practical, future aircraft could adopt the technology widely. Airbus continues developing natural laminar flow designs. NASA research advances understanding of how to make laminar flow work operationally. Material science provides new surface treatments that resist contamination better. The next generation of aircraft might incorporate laminar flow extensively. If researchers solve reliability challenges, the efficiency benefits become too significant to ignore. This would make today's aircraft obsolete rapidly. A 10 to 15% efficiency advantage creates enormous competitive pressure. Airlines operating laminar flow aircraft would have substantially lower costs than competitors flying conventional designs. Boeing cannot afford to fall behind if laminar flow becomes practical. The company invests in research. They develop expertise. They prepare for the possibility that breakthroughs make the technology viable. But until reliability matches efficiency, Boeing will not implement laminar flow on production aircraft. The company learned hard lessons about deploying technology before it is truly ready. The 737 MAX crisis demonstrated the catastrophic consequences of prioritizing innovation over proven reliability. Boeing will not repeat that mistake with laminar flow wings. The technology must prove itself thoroughly in real-world conditions before Boeing commits production aircraft to it. So we reach an interesting moment in aviation. Revolutionary technology exists, it works in testing. Benefits are substantial, but practical implementation remains just beyond reach. Laminar flow wings represent aviation's future, potentially. They could transform efficiency fundamentally, but they are not aviation's present because reliability requirements remain unmet. Which means the next generation of aircraft might look very different from today's designs. Wings shaped entirely around maintaining laminar flow. Manufacturing processes prioritizing surface perfection. Maintenance programs focused on preserving aerodynamic smoothness. Or perhaps researchers will conclude laminar flow can never meet operational reliability requirements. The benefits, while real, cannot overcome practical limitations. Aviation will find efficiency through other technologies instead. Boeing is not ignoring this revolutionary wing design. The company is waiting, watching, researching, preparing for the possibility it becomes viable while refusing to deploy it prematurely. The revolutionary wing exists. It works, but it does not work reliably enough yet. When it does, Boeing will be ready. Until then, the most efficient wing design ever developed remains grounded by the gap between laboratory perfection and operational reality.